All right, everybody. Today we're going to be talking about section 1-4 in your textbook, which is about something called the trapezoid rule. You'll notice that I've made a little note sheet for us. You should print out the note sheet and do your work on here. However, you'll notice that I'm at home. I don't have a printer at home, so I will be writing all of my work here on a separate sheet of paper. Okay? Cool. So with that in mind, here's the motivation for today's lesson. In the last class, I taught you about something called the definite integral. And here's what the definite integral did. It allowed us to find the total change in something when we were given the rate. For instance, if we were given the velocity at which an object is moving over a period of time, we could use it to find the total displacement or the total distance traveled by that object. Now, the good thing about the method that we used last time was that it was pretty easy. What we would do is we would draw a little rectangle, and then we would estimate the area of that rectangle, and we would use that to represent our total change. The bad thing about that method is that everybody was getting different answers. Well, we're going to fix that problem today because with the trapezoid method, everybody gets the same answer. Let's begin a problem. It says here, Star Wars Episode 1-4, a new miracle. Or is it numerical? Rocket problem. Or is it a rocket problem? More on that moment. Elevator, Darth's lovely daughter, is flying her rocket ship. At time t equals 0 minutes, she fires the rocket engine. The ship speeds up for a while, then slows down as Alderon's gravity takes effect. The ship's velocity in miles per minute is given by the function v of t equals, you can see the equation written right there. So here's the situation. We have the velocity of an object again, just like we did last class. I want you to type that equation into your calculator, and then I want you to get a graph of it. I want you to use as your window for the x from 0 to 8, and I also want you to use something called zoom fit. Let me show you how to do that. Here we are. Here's the equation. I am going to go to y equals, and under y1, type in x to the third power, take away 21 of those x squareds, tack on 100 of the x's, and then add 110. So there's our equation. Next thing is you go to window, and under window, for the x min, you're going to choose 0, and for the x max, you're going to choose 8. And the reason we're doing that, by the way, is because we're interested in the velocity between time 0 and time 8. Now, what we don't know is what all the velocities are, or the y values during that interval, right? So when I come down right here, I don't really know what to select for my y min and my y max. So what I'm going to do instead is I'm going to come here to the zoom button. When I get to the zoom button, I'm going to go down right here to what calls zoom fit. Here's how zoom fit works. This is cool. It takes the interval that you gave it on the x, so from 0 to 8, and then it calculates what's the smallest and what's the largest y value on the interval, and then it automatically makes that the range on your calculator. So here we go. All right, so there it is. There's the graph of Ella's velocity over time. Now I am going to make one change. I want to be able to see the x-axis. So I'm going to change the y minimum to 0 so that I can do that, and I'm going to hit graph one more time. And there it is in all of its glory. All right, so with that in mind, let's go back to the story. Ooh, that rhymed. All right, so let's see. What does it say here? There is something dangerous I neglected to tell you. At t equals 0 minutes, the autopilot switches on, and Ella loses control of her rocket ship. It begins barreling towards the desert, which is 1,520 miles away, when the autopilot takes control. Ella needs 8 minutes to climb under the control board, unscrew the safety panel, and rewire the system so that she can retake command of the ship's computer. However, by t equals 8 minutes, the ship may have already crashed. Ooh. So here's the question today. We want to know whether the ship is going to crash or not. which means that we want to know the total distance that the ship travels from time 0 to time 8. And my question is, how are we going to decide whether she survives or not? Okay, so that's Q1. Well, hopefully you figured out that we need a definite integral for this. So if we're going to write a definite integral, we know that this means we are summing up all that area, starting at time 0 and ending at time 8, where the velocity is multiplied by time. Yeah, okay, Mr. Klein, that makes sense. If you take velocity and you multiply it by time, that gives you distance. We're adding up all the little distances she travels over those 8 minutes. And let's see. Suppose this was to be smaller than 1,520 miles. Well, then sign her up for the next Star Wars movie because she survives. However, if we were to calculate this quantity and the number that we get is larger than 1,520 miles, she crashed. And sorry, folks, the saga is over. So that's how we're going to make our decision. We're going to take this graph right here, and we're going to find the area underneath it today using the trapezoid rule. All right, here we go. So steps. Step number 1 is that we want to divide this area below here up into a bunch of trapezoids. And anytime you're given one of these problems, I'm going to tell you how many trapezoids. And for today, we're going to say 4. Or in other words, n, our number of trapezoids, will be equal to 4. So the first thing that you want to do is you need to figure out what is the change in time, or the change in x, going to be for each one of our intervals. And the way you do that is you say, well, my change in time is going to be equal to the total change in time, which is from 8 minutes to 0 minutes. And then I'm going to divide that by the number of trapezoids that I need, which in this case is 4, which means that each one of our trapezoids is going to have a width of 2 minutes, or a height of 2 minutes. Okay. In general, what I just did right here is I used this formula. Make sure you write this down. The change in x for a trapezoid will always be end value minus start value divided by number of trapezoids. 8 minus 0 equals 4. Okay, so we've got our number of trapezoids. The next thing I want you to do is draw a picture of what it looks like. So if we come over here, you want to grab yourself a marker or a colored pencil or something like that, and just make a little vertical. Oh, that was bad. I broke a glass. I'll try not to step over there. Okay, so you've got these subdivisions here, and here, and here, and here, and here. And I think it's probably pretty clear to you guys, because you guys are some smart cookies, but just to make it clear, I'm making it so that each one of these changes in x down here has a width of 2, because this was 2. Okay. And now the way that you actually make the trapezoid is by taking these points. So these would be the velocity of the ship at time 0, and then 2 minutes later, and then 2 minutes later, and then 2 minutes later, and then 2 minutes later. And you connect those, and that makes a trapezoid. You connect that one, trapezoid. Okay, and so the idea is that if we were to find the area of this trapezoid in this one, and this one, that would give us not a perfect, but a pretty good approximation of the area under the curve. And once again, we know the area under the curve, in this case, represents the distance, okay? T4, it represents the trapezoid rule with 4 trapezoids. And I know I'm going to need 4 of the formula. So let's write those out. Now, do you remember the formula for the area of a trapezoid? You do? Good. You remember that it is 1/2 of the height of the trapezoid multiplied by the sum of the two bases. So like for the first one, this would be the height of the trapezoid. It's easier to see if you turn it this way, right? And then these two parallel sides right here would be the bases. So we have 1, 2, 3, 4 trapezoids. So I'm going to need 4 of these. Mr. Klein, when I'm doing my work, do I need to write all of this out, or can I just put it into the calculator? Excellent question. You always, 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 always want to write this out. I want to see this work when I look at your paper. Okay, so for the first one, I can see pretty clearly that the height is 2. I'm going to go ahead and fill in a 2 right here. Now, I need to know what the bases are. And I can kind of estimate. This one looks a little bigger than 100. And this one looks like it's, I don't know, about 225. But I don't want you to estimate. I want you to give them to me exactly. And there's a way that you can give them to me exactly, and that's this. You can plug those times into this equation. So for instance, if I was to plug 0 in here, it would make all of this go away, and we get 110. So I know that this base right here is 110. I'm going to fill 110 in right here. If I wanted the length of this base, I could plug 2 into the equation. Now, here's what I don't want you to do. I don't want to see you going 2 to the 3rd power minus 21 times 2 to the... No, don't do that. Use the calculator to your benefit. And recall that we already have the equation typed into y1 right here. And so there's a couple different ways that you can get the answer out. One is you can go alpha trace y1 at 2, and that will give you that it's 234. So I'm going to put a 234 right here, and I'm going to put a 234 right here. Now, that is not the only way that you can do it. Here's another option. I think this option is pretty cool, and that's that if you go to table set, under table set, I want you to come over here and select ask, just for the independent. And once you've done that, I want you to hit second, and then I want you to hit table. And if there's any values in there, you can just hit clear. Actually, it's not clear, is it? It's delete, 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 delete. So it's nice and empty. And now all you have to do is fill in the x values you want. So for instance, I want the x value at 0, and at 2, and at 4, and at 6, and at 8. All right? So when you're doing these, type the equation in, plug in the times where you want the values, and then let's fill these in. 234, 238, 170, and 78. Once you've got that good, it's time for you to fill in the rest of the trapezoids. So this one right here has a base of 2, and the heights are 234 and 238. This one right here has a base of 2, and the heights are 238 and 170. This one right here has a base of, or a height of 2, and the bases are 170 and 78. All right, so that's basically it, folks. All you need to do now is take this stuff right here and plug it into your calculator. All right, so one thing I want you to note is that if you did plug it into your calculator, see how the half and the 2, those would just cancel out, right? Okay. And the other thing I noticed is that we got one of these, 2 of these, 2 of these, 2 of these, and 1 of those. So I might just go ahead, and as I'm typing into the calculator, I might do it this way. I might say 110 plus 2 times 234 plus 2 times 238 plus 2 times 170 plus 78. And it will always be that way. You might not have a 2 right here, but you can always do that with these bases right here. And then I think about that, it kind of makes sense, right? Because you've got 1 of both of the ends, and then you've got 2 of all the ones in the middle, because all the ones in the middle are on more than one trapezoid. So I hit my answer, and I get 1472. And let's see, this is about miles. And oh boy, oh boy, oh boy, ladies and gentlemen, Ella lives. It's only 1,472 miles, which means that we can sign her up for the next movie. And oh, yeah, there's something I don't like. There's something I do not like here. Is there something that you don't like? Look at these trapezoids. They're missing some of the area, aren't they? What does that mean about this number? This has to be an under approximation. Which means the actual distance she traveled is larger than 1472. I don't think we're out of the woods yet. All right, so come on over here. How do we know whether we're going to have an under approx over or an over approx? It's pretty simple, really. It's the difference between having something that looks like this and something that looks like this. If your graph has this downward shape, notice that the area is going to be missing some of the area you need. And by the way, if it has this downward shape to it, remember that we call this concave down. Down like a frown. And then right here, let's build some trapezoids. I know I'm not making them exactly the same size. That's okay. Notice that here it's catching too much area. It's going over what we want. And if it's too big, that's going to give us an over approximation. Remember that if it's opening up like this, up like a cup, we say that it is concave up. All right, so now you know when you look at the graph, you'll be able to tell whether it is an under or an over approximation. What do we do about this? Well, here's the answer. What was the decision I made for you at the beginning of the problem that we could have changed? It was the 4. I told you to make 4 trapezoids. If we wanted a more accurate measurement of the area under this curve, what could we do with that number of trapezoids? We could make it. Now, I know what you're thinking to yourself. Oh, Klein, are you going to make me calculate 10 of these, 20 of these, 100 of these? No, you are in luck. Check this out. If you go to Canvas, you can pull up a link to this guy right here, right? This is a trapezoid calculator. All you need to do is start by typing in the equation. One thing I want you to be careful about is that you need to use the star as a multiplication sign. It won't accept 21x. It has to be 21 multiplied by x squared. Then you can put in here 0 and here 8. And then let's suppose we wanted just one trapezoid. Here we go. Give us the answer. All right, so right here, you can see the width of the trapezoid was 8. And then right here, it did one calculation and it came up with an answer, and that was 752. All right, so now let's kick up the number of trapezoids. I'm going to go to, let's see, we already did 4. Let's go to 10. This time, I like this because you can see all that work that you did not have to do. And at 10, it's 15, 12, 32. All right, so our buddy Ella is still safe. Let's see, 1 trapezoid, it was 752. 4 trapezoids, 1472. 10 trapezoids, it was 1512. Let's go 20, and then let's go 100, and let's go 1,000, and then let's see what happens, okay? So I punched in 20, 151808. We are still safe. Way to go, Ella. Let's go higher. Let's go to 100. $1519.9. Oh my goodness, look at all those calculations. Just for giggles, let's go to 1,000. I don't even know if this thing will handle 1,000. Oh, it did. 1519.999. And let's see. Ooh, thank you, computer, for doing all that work for me. We can see a pattern here as the number of trapezoids increases. Specifically, if Tn is the number of trapezoids, and we're taking the limit as n becomes larger and larger and larger, what does it look like that number is? That's right. It's 1520. So the limit as the number of trapezoids goes to infinity is equal to the actual area under the curve, which in the case of this problem is 1,520 miles. So does she live? Does she die? I don't know. We made up a rule, and it didn't take 1520 into account. There's the trapezoid rule. Good day.